So, okay, so I'll try to finish more or less in half an hour. Should start this actually. My talk will be in two parts. I'll give a brief overview of Mellin Space and some of the work that has been done in this field. And then I'll turn to our own work and report on the main results that we obtained. So, Mellin space representation is a particularly nice representation for conformal field theories, which was proposed by Mack, who was one of the early pioneers of conformal field theory in the 1970s, and he wrote this paper in 2009, in which he developed some of the main properties and emphasized the importance of Mellin space. In a computational framework, actually, this representation occurred also in an earlier paper of Symanzik, in which he did some calculations in conformal field theories. But at that point, its significance wasn't noted. So the Mellin transform, so this is something which Ananda also mentioned yesterday in the context of doing bootstrap calculations. And my focus would be somewhat different. Anyhow, let me just go through some of the basic things. So the Mellin transform is some linear integral transform on some function f. S is the Mellin variable, and there are conditions you put on the function and so on, which I won't be talking about here, but you can define its inverse. This is the contour integral in the complex plane. C is some small positive number. This is to shift the contour away from the singularity at x equal to 0. Now this integral transform, as pointed out by Mack first, it's particularly useful when you are dealing with scale invariant theories. And in the context of conformal field theories in particular, Mack gave the following Mellin space representation of conformal field theory correlators. So this object here is some connected endpoint correlation function of scalar operators in a conformal field theory. And so this is the Mellin this object here is what's called the Mellin representation of the CFT correlator, or also the Mellin amplitude. These gamma functions are introduced for reasons of convenience. I and j labeled various points. So if you're dealing with an endpoint correlation function, then you can do a counting of the parameters, and basically when you draw n, when you're drawing pairs of unordered pairs from endpoints, the number of ways you can do that is n into n minus 1 by 2. And then it turns out that there are further constraints on these Mellin variables which come from conformal invariance, the linear constraints. When you do a full counting of the number of independent Mellin variables, this number turns out to be n into n minus 3 by 2, which incidentally is also equal to the number of conformal cross ratios for endpoints in some conformal field theory, and the number of independent Mandelstam variables for an n-particle scattering amplitude. So this already hints at some relation that this might have with scattering amplitudes, and I'll talk a bit more about it in a while. So now you can actually incorporate these constraints in a natural way if you define these auxiliary momentum variables k, so that the Mellin variable Sij is ki dot kj, where this vector has norm equal to the conformal dimension of the ith primary external operator, and you have an overall conservation of this Mellin momenta at each vertex. You can specialize to n equal to 4, so you have 4 external points. You're dealing with a 4-point function. And then it turns out to be convenient to define these variables, S and T, which are some linear combinations of the 2 independent Mellin variables in this case. These are the dimensions of the primary operators, the 4-point function. And so when you write the Mellin transform in terms of these variables, you see that these S and T variables, which are like the Mandelstam variables, they the conformal cross ratios. So you know that the 4-point function is given in terms of conformal cross ratios, two independent conformal cross ratios. And the Mellin variables S and T are effectively the Mellin transform of these two objects. And so the 4-point function in conformal field theory has a Mellin transform, which we'll denote by this. Now there are various properties of, various nice properties of the Mellin space representation, which was pointed out by Mac. So for example, this object M is a meromorphic function of the Mellin variables. So it has only isolated simple poles, and the simple poles occur where you have some primary operator being exchanged. So it gives you the conformal dimension of the primaries. This is something which follows on very general grounds from properties of the conformal OP, and also related to the fact that conformal field theories in dimensions greater than 2 have a discrete spectrum. So you only have, you don't have any branch cuts, you just have simple poles. Furthermore, there is, if you look at the residue at these poles, these, for example, for a 4-point function, if you look at the residues, then these are related to the OP coefficients. And therefore, the Mellin amplitude manifests the CFT data in a very natural way, with the poles corresponding to the conformal dimensions, the spectrum of the operators, and then the residue of the poles giving you the OP coefficients. And Mac showed that on general grounds you can, for example, you can do an S-channel expansion of this Mellin amplitude. And this is just what I said in words earlier. So you know you have, this is the conformal twist of the operator, which is exchanged. So tau L is just delta in the conformal dimension minus the spin. And these are some 3-point coupling constants. This is a polynomial in T of degree L, where L is the spin of the exchange operator. And then this is summed over various descendant terms. And poles only depend on? No, this is an S-channel thing. So you can do this thing in the T channel, and then you will have S here and T here. And this is very analogous to what happens for the case of scattering amplitudes. So in fact, you know, the crossing symmetry of the CFT correlator manifests itself. So when you swap S and T, you have a channel duality. And that is essentially the same thing as the crossing symmetry of the CFT correlator. So all of this is suggestive of the fact that there is some analogy between these Mellin space CFT functions and scattering amplitudes. And of course, so far all we have done is that, you know, you're looking at correlation functions in position space and transforming it to Mellin space. So it's not clear that in itself it has anything to do with scattering amplitudes. But this comes about. Is there a question? No, so there is a pole for every primary, and there are these so-called satellite poles. So there are poles for every primary and each of its descendants. So N labels the descendant here. Yeah, the sum over N is over all descendants, and L, okay, so this is a label of the primary. Yeah, I mean, even these, so for example, these coupling constants, you only need to know only for the primary. The ones for the descendants are also fixed. Yeah. So just to set our own work in context, and also because this is of some interest in its own right. Sorry? So QLT, I think, are just these hand polynomials which Ananda was talking about yesterday. So yeah, I think, and they, yeah. And they reduce to Legendre polynomials, the flat space limit, and so on. So, okay. So there's been some work on the Mellin space representation in the context of AdS CFT. And so let me just briefly talk about this. So as is very well known, in AdS CFT, you compute CFT correlators at strong coupling and at large n by computing Witten diagrams in some supergravity theory in AdS. Now you can do these computations in Mellin space, as was done by all of these people, and one finds that there are considerable simplifications compared to position space computations. So after AdS CFT, there was a lot of work was done on doing these Witten diagram computations, and even the very simple computations actually turn out to be quite technically involved in position space. But if you do the same computations in Mellin space, things are very simple, and you can see that, for example, the CFT correlators are, the Witten diagrams correspond to very simple rational functions of the Mellin variables, which is what I alluded to in the earlier slide, that the structure is much more simpler in Mellin space. And diagrammatic rules, the Feynman rules were developed for these AdS Witten diagrams at tree level for scalar exchanges, which enabled you to write an endpoint function in the CFT at strong coupling in terms of some simple Feynman rules you can have for any given diagram, any given Witten diagram. And what is more, you can actually, the analogy which I was referring to about the scattering amplitude and the Mellin space correlator, you can actually put this on a firm footing. So there was this very interesting relation which showed by Penedones, that you can actually define, you can give a definition of the flat space S matrix of n massless particles in terms of an integral transform of the Mellin space CFT correlator. So this is what it looks like here. So this is the scattering amplitude, or actually its connected part, the T matrix. These curly Sijs are the Mandelstam invariants, and you work in D-dimensional, D+1 dimensional flat space. And here on the right, everything expressed in terms of CFT data. So R is the AdS radius, which is taken to infinity, it's the flat space limit. And there is this integral transform. You rescale the Mellin variable by this object, and you take this particular integral transform, and that defines for you the flat space scattering amplitude. So yeah, so this was more or less an overview of some of the work which has been done here. So I thought it might be useful and put things in context. So I'll talk next about our work. And are there any questions at this point? Okay, so let me turn to our own work. So, I talked about using Mellin space for AdS CFT computations. Now, Mellin spaces are probably also very useful for implementing the conformal bootstrap and extracting non-perturbative information about conformal field theories. But one legitimate question you might ask is that there are perturbative conformal field theories, and which has some weakly coupled Lagrangian description, and you might just want to do perturbation theory, just like you do in regular quantum field theory. And now, given the fact that Mellin space is tailor-made for conformal field theories, you might want to study conformal perturbation theory in Mellin space and see if it has any nice features. So this is what we do in this project. So the goal is to develop Feynman rules in Mellin space. So to start with, at tree level and for scalar fields. So we have just taken a few steps in this direction. There are many things which need to be done. And just to contrast this with what I just mentioned in the AdS CFT case, here this will be a weakly coupled CFT, and we don't use AdS CFT. So there's been some work, some related work. So Paulo, Stradlin, and Volovich developed the Mellin representation of dual conformal integrals for n equal to 4 super Yang-Mills amplitudes, perturbative amplitudes. So as is well known in n equal to 4 super Yang-Mills, you have this dual conformal representation. So if you look at the amplitudes in momentum space, because of momentum conservation, you will form a closed polygon of the momenta, and the vertices, the coordinates of the vertices parameterize a space, which is the dual conformal space in which there is a dual conformal symmetry which acts. And it's useful for doing various computations. So these people looked at the Mellin representation in this dual conformal space. So it's not exactly what we are doing, but it's for perturbative n equal to 4 super Yang-Mills amplitudes. Anyhow, so you just start with a tree-level position space CFT correlator. So you know what the two-point function, of course, is, and you built a whole this on the blackboard here, for example, is some tree-level correlation function in position space, and just as you do in usual quantum field theory, you write the amplitude by integrating over all internal vertices. So the internal vertices are labeled by U. These label the external vertices which are connected to all of the U's. And so you have to integrate over all the internal vertices to get the position space correlation function. Now, sorry, so gamma A, okay. So gamma A is delta is the conformal dimension of the externals. Let's say there are n external points. So delta is the conformal dimension of the external, so I labels, I should probably explain the notation a bit. So A labels these different vertices here, and at each of these vertices, you can have external operators connected. And so gamma is the conformal dimension of these internal lines. This is a tree-level thing, so gamma is not really undetermined, because at each point, at each vertex, you will have a conformal vertex condition, which I'll talk about. And so gamma is not really undetermined. For a loop, it will be. Yeah, so you can think of a massless 5 to the power 4 theory. Deltas and gammas are always, I mean, in interacting field theory, you can have anomalous dimensions. So what we are doing is, so what we'll be doing here is that, there is a free conformal field theory, where of course these will all be integers, and then we'll consider a perturbation. And so there will be a weakly coupled conformal field theory, which sits close to the free CFT. And now it is true that generally you don't have, if you consider a free CFT, even if you introduce a marginal coupling, most of the time you don't end up with the conformal field theory. The conformal invariance is broken. So this is true only for a very restrictive class of theories. But anyhow, to start with, we just deal with, so you can think of 5-4 theory if you want to. And yeah. This is not a conformal block expansion. Yeah, these are correlation functions. These are not amplitudes. So the thing is that, of course, when you write a CFT correlator in Mellin space, so I'll be using these terms interchangeably. What I'm really looking at is the position space correlator, and then looking at the Mellin space representation of it. This is also sometimes called the Mellin amplitude, but it's an amplitude really only in this dual AdS sense. It's not really a, yeah. Yeah. Okay. Okay, so we are not looking at, we are looking only at those fields which, in some weakly coupled Lagrangian description, they occur in the Lagrangian. So they are fundamental fields in that sense. No, so this is true. I mean, this is the, here it's right, yeah. So delta will be an integer because it's just like in ordinary quantum field theory. When you do perturbation theory, the propagators you use are just free field theory propagators. And it's the same thing here, so that is right, yeah. Sorry, what intermediate, guys? Elementary fields which occur in the Lagrangian. So right now think of some, like Suvrat said, think of Pfeiffer theory, for example. There are some elementary scalar fields which occur in the Lagrangian description of the theory. And these are what are there in this Feynman diagram. Okay. Uh-huh. Yeah. Okay. So, okay, so you start with this position space correlator and you are interested in finding, sorry? Yeah, I'll talk about it. So basically the sum of the dimensions of all scalar fields at every vertex has to be equal to the space-time dimension. That follows from the fact that there is conformal invariance. So if you look at the action of the special conformal generator, it will tell you that at each point this has to hold for conformal invariance to be unbroken. No derivative interactions here. So, okay, now for quantum field theories in momentum space, so this is one of the main reasons that the momentum space is useful for weakly coupled quantum field theories. You find that at tree level, an object like this factorizes into a product over propagators. And therefore, rather than looking at something complicated like this, in a regular quantum field theory, you just look at a product over propagators and vertex factors, the usual Feynman rule thing, basic elementary thing you do in quantum field theory. So you can ask the question that I'm starting with this correlation function, position space. I'm interested in finding its Mellin space representation. And does it also have any similar features? In particular, does it factorize? So so I won't give many details. Some of the computations were rather tedious, and I think I'll just mention the results we get. But let me just give a brief outline of how we do the computation. So the point is that you introduce Schwinger parameters. So this is a trick which is used often in computing loop amplitudes in quantum field theory. So the point is that you have these propagator factors, which are like 1 by x minus y to the power something. And you use this representation, which basically exponentiates a propagator. And you use this for every such internal line. And once you do that, you're left with some Gaussian integrals over the internal vertices. So you have to integrate here over all the internal vertices. You turn all of these things into exponentials by using this identity. And then you can do these U integrals, so just Gaussian integrals, some n-dimensional Gaussian integrals. So I won't give the final result, but you can just do them. So this is basically what I'm outlining how we did most of these computations. In a similar, simpler setting, some of these calculations were done earlier by Symanzik and Paulo and others. But we need to do some additional things to get our results. So now you have to do some further manipulations. You introduce a delta function in variable v. You do some v-dependent rescaling of the Schwinger parameters. And then you impose these conformality conditions at each vertex. At each vertex, all the scalar fields at each vertex, the conformal dimension must sum to the space-time dimension v. Okay, and So at this point, you had introduced these integrals, these Schwinger parameters. You can then do the Gaussian integrals. You'll be left with some exponentials. And now you carry out what's called like Symanzik trick, which is just, you write these exponential in terms of these, what's called the Kahan-Mellin integral. This is just saying that the exponential function and the gamma function are Mellin transforms of each other. And this is how you introduce the Mellin variables. So for each exponential factor, you will get a Mellin variable. And so the final result will schematically look like this. Okay, and if you compare with the definition I showed for the Mellin amplitude, this integral over Schwinger parameters, so this object here, product over all these. So this T is a Schwinger parameter, and this object here will give you the required Mellin amplitude, which you want to calculate. So this is an elaborate calculation. I won't give the details. Let's just look at some simple cases. Consider a contact diagram, which is just a cross diagram. There you can easily show that this is a trivial integral, and you just get m to be 1. It's the counterpart of the fact that in momentum space, if you look at a contact diagram, that just gives you a vertex factor, basically just a constant. So this was done like by yeah. No, but all these are connected correlation functions, and it will be amputated. So there will be when you do these, you will get. I mean, there are these Schwinger parameters. So there are Schwinger parameters for the internal lines, which I label by T. There will also be, which I have not written here. There will be Schwinger parameters over the external lines, which for the connected part. And there will be an overall delta function, which will yeah. No, I'm just referring to the fact that, for example, if you look at, I don't know, phi cube theory or something in 4 dimensions, which has some small coupling constant, and you do Feynman rules, then that coupling constant is the only vertex factor that you get for a. Okay. Yeah. So. No, but so one thing I haven't mentioned is that this measure here, I have these bracketed factors. This already includes the delta function part, which you get after amputation. So what I'm defining here, this object, by definition, is the external legs have been taken away. Yeah. No, so when you do this, these manipulations, that leads to a delta function which enforces this constraint. Well, position space is okay. All right. So anyhow, let's look at the propagator next. So this is you look at an S-channel diagram where you have. So this is again a simplified form of this computation you do for a single internal propagator, and you can do the computation. You obtain a beta function, which has poles when any of the arguments is a negative integer, and therefore You can also write it into some form where it is manifest that there are these poles which occur corresponding to the exchange primary, which has conformal dimension gamma, and all its descendants. So this is for simple cases. Now you can look at an arbitrary tree diagram like this. This probably looks a bit too symmetric, but anyway, take any tree-level diagram like this one on the board. And so just to emphasize, this is a skeleton diagram in the sense that I haven't included here, I haven't drawn the external vertices which might be attached to these points. And so you do a similar computation, which is much more elaborate. So you have to deal with some nested Schwinger integrals, which you can. So we did this this was done in two ways. One is a straightforward way, the other is by using what's known as the Mellin-Barnes representation. But anyhow, the final result is that you indeed do get a tree-level factorized form for the Mellin amplitude, which has a nice diagrammatic interpretation. So you basically just need to include these beta function factors for each of the propagator. And this Mellin variable Si is just the sum of, so if you look at an internal line like this, then you just have to consider the total Mellin momenta flowing into it, which is this object, and you take the square of that. That is the Mellin variable which occurs there. And then you take the product over all such propagators, and that gives you the Mellin amplitude that you are dealing with. And so again, this result is similar to what you have for tree-level momentum space amplitudes in quantum field theory. You just have to deal with products over propagators. So I haven't given you all the technical machinery which went behind the proof, but I think that should be sufficient. Now, this is something which we haven't managed to do yet. So you might want to do one-loop diagrams in a similar way. And indeed, the calculation I showed you here, this you can do for loop diagrams also. So you will obtain a Schwinger integral representation for the loop amplitude in a similar way. Now the question is whether you can recast it in a form where you can give some diagrammatic interpretation. So there what you would generally have would be, you would have, consider for example this 4-point function, box kind of a diagram. You might have an undetermined Mellin momenta flowing inside the loop, and then you might want to express this amplitude, this one loop amplitude, as an integral over one or more Mellin variables. And then in the integrand, you would want to have a product over all the propagators, just like you have in ordinary quantum field theory. You have an undetermined momenta in a one-loop diagram in a usual quantum field theory. And then you integrate over this loop momenta to get the one-loop amplitude. So we were able to manipulate this and convert this into some contour integrals, but we didn't manage to get it into a nice form where you can have this nice diagrammatic interpretation. If you could do this, then there is a hope you can do some conformal perturbation theory at higher loop order in Mellin space. Okay, this will be my last slide. So there isn't that much to say here. This is some preliminary results we obtained for the Mellin representation in non-conformal settings. So now, so Mack in his paper briefly speculated about the use of all this for a field theory where you do not have conformal symmetry. And here, of course, it's not clear that because it's conformal symmetry which gives you all the nice properties of Mellin amplitude, and uromorphicity, and all those things. So that will probably go away, but just as a purely academic exercise, you have some position space correlation functions, and you have a well-defined mathematical transform. So you might want to see how usual things look in Mellin space. So now consider a free conformal field theory, and now consider some generic deformation, generic scalar deformation, which might break conformal invariance. And now you're interested in finding the Mellin representation of correlators in such a conformal field theory. So you relax the conformality conditions. So this object, which was 0 first, is some, so A parameterizes the vertices, and so you have some additional parameter which is there. And So basically what we did here was just, I showed you the propagator in a weakly coupled conformal field theory. The propagator in Mellin space looks like a beta function. So you do a similar computation, again a tree-level S-channel diagram, but now you relax these conformality conditions and you can do the same exercise of computing these integrals and converting them into the Mellin representation. And okay, so it's some complicated answer. The details are not really that important. So the important things are it's some 3f2 hypergeometric function. I haven't told you what all these symbols are. So R's and rho's are some linear combinations of the various Mellin variables. So it's expressed as some combination of various Mellin variables. And the other thing which you can check is, again, as you would expect, when you take these lambdas to 0, then this goes to your beta function. And these external leg factors, these gamma functions, when you do this carefully, they give you some delta functions which impose the, so to speak, the on-shell conditions, which is that the Mellin Momenta has norm which is equal to the conformal dimension. So, okay, so this, I just wanted to show this, that you can do this computation in Mellin space. You get a 3f2 hypergeometric function for this non-conformal case. When you do this in the conformal setting, you obtain a beta function. And so just on a side note, probably something not directly related to this, as I mentioned that this Mellin space computations have been done for AdS CFT correlation functions, and exactly the same, the amplitude for, the Mellin amplitude for this S-channel exchange diagram for a strongly coupled conformal field theory with scalars being exchanged was computed by Paulo. It's again some 3f2 hypergeometric function in terms of the Mellin variable. It's probably not related to this, but anyhow, the forms of this are known, so it might be interesting to see how you might interpolate between these various results. And anyhow, there are various conceptual issues which are which we are still struggling to understand in this whole setup. But I just wanted to show at least one computation in this setting. And it might be the case that indeed Mellin space has some utility in a non-conformal setting. So let me just end. So I told you about tree-level Feynman rules for scalars, which you can develop in Mellin space in analogy with momentum space Feynman rules for regular quantum field theory. And you have this nice factorization property at tree level. So just a few last comments about future work. So we did this all for scalar operators, and one, of course, be interested in incorporating spin. So, for dealing with tensorial and spinorial exchanges in these diagrams. More interestingly, I guess, is dealing with loops and whether you can get a nice diagrammatic approach to dealing with one-loop diagrams. And as I already mentioned, further exploration of the utility of Mellin space in non-conformal settings. Okay, so that's all I have to say. Thank you.
At various places. So have you computed that? Like, is it similar to the tree level or something different? Like, when you take a loop with various external diagrams.
You mean like this? Yeah. So this one, this we haven't managed. We haven't managed to, in the sense that you can of course write an expression which involves integrals over Schwinger parameters. So it's some explicit expression. But the point really is, you want a diagrammatic set of rules. You're dealing with a weakly coupled CFT, and you want to have a diagrammatic conformal perturbations theory. So you want to be able to look at a diagram, identify its constituents, and write various factors and integrate over undetermined variables and so on. So we have not managed to manipulate the result in that form.
Oh, you're not looking, I thought this diagram was more for if there is a loop in between a propagator.
No. So
like a
You can of course have.
say 5-cube theory, 5-4 theory.
So you can have a diagram like
Yeah.
this, of course, right? And in such cases, it's much easier. I mean, these one-loop results were discussed by Penedones actually in this paper. And so, for example, for diagrams like this, it's actually much more easy. You just have to sum the conformal dimensions and you are done. But when you're dealing with loop diagrams like that, that's where it becomes non-trivial. So,
but that is of more importance, right? Like
no, I mean,
usually like.
No, I mean, these are both loop diagrams. I mean, they will.
But you know the results for that.
Yeah, this one is, because you just have to sum the conformal dimensions and it's easy to get. But for that kind of a diagram, again, just to reiterate, I mean, the expression is of course known, you know, you just have some integrals over Schunke parameters, that's known. But to be able to get a diagrammatic interpretation, as we can get a nice diagrammatic interpretation at pre-level. But for this, we didn't manage to do that yet. Well,
worry about Lagrangian usual conformal perturbation.
Well, I mean, it depends. If you're doing like an epsilon expansion or something, it might be different. But you know, you might be dealing just with. There are a large class of conformal field theories which do have a Lagrangian description. Right. And so this is for that. You know, you need a weakly coupled Lagrangian which has some fundamental fields. You draw a Feynman diagram which has these fields, latest components, and that is what we're addressing here. So you do need a Lagrangian to enter these. I mean, it's just like regular quantum field theory. The only thing is that that theory happens also to be conformal.